Okay, so we're going to talk a little bit about solutions. So I have a few definitions up here which are going to be pretty useful. So first off, a solution is just a homogeneous mixture of two or more substances. And when we're talking about substances, we're going to be talking about elements or compounds. And they're going to be in a single phase. Now a phase is going to be the three phases we've talked about in the past: solid, liquid, or a gas. But something important to realize in this particular topic is that although we'll be talking about liquid solutions most of the time, solutions can actually be in other states as well. So for example, it could be in a gaseous state like air. Air is technically considered a solution because it's made of different components. So these components here: nitrogen, oxygen, carbon dioxide. Carbon dioxide, of course, is a compound. Nitrogen and oxygen, they are diatomic, but they're made up of elements, single elements. And in a solution, there are two major components that you need to know. One of those being the solute and the other one being the solvent. Now the solute is going to be whatever component of the mixture is in the lower amount or the lesser concentration. And the solvent, that's going to be the component of the mixture that's in the greater concentration or the higher amount, and that will be dissolving the solute. So a real classic example would be salt water. So salt would be considered the solute, and the water would be considered the solvent. So when you take some salt and you dissolve in water and you stir it all up, you've got yourself a solution. You've got a homogeneous mixture, which just basically means it's a uniform mixture. The salt is evenly dispersed through the solution, and the salt dissolved by the dissolver, which in this case is going to be the water. Water, for most of the problems we're going to deal with, is going to be the solvent. Sometimes it's referred to as the universal solvent. So salt dissolved in water, solute dissolved in solvent, you end up with a solution of salt water. Now, one of the most popular calculations that you'll encounter is something called molarity. And molarity is a way for us to measure the concentration of a given solution. And molarity is going to be represented by a capital M. And it's simply equal to the amount of moles of the solute per liter of the solution. And there's a couple different ways to write this formula. One of the more common ones that I see is usually the second version, which I have up here: molarity equals moles divided by liters. It's very important that you realize that volume has to be expressed in liters and not milliliters. So if you ever have a problem, encountering a problem or a calculation where they give you milliliters, you'll have to convert it to liters. So what I have here below is basically just an example problem, and it's already calculated for us. But the question asks, what is the molarity when a 0.75 moles is dissolved in 2.5 liters of solution? So this is a pretty basic problem, definitely entry level, but you can kind of see how you calculate it. Well, moles will be in the numerator, and liters has to be in the denominator. And again, they give us moles and they give us liters. So it's pretty simple. We'll just plug it in into this fraction and we'll solve for molarity. In this case, the answer is 0.300 moles. I'm sorry, molar. Molar is how you would say that. That's something else we'll need to talk about. So you don't say 0.300 molarity. You'll say molar instead. So let's look at an actual problem where there's a little bit more going on. And so we're going to crank up the difficulty just one level here. This particular one, you can kind of see that it's a bit different than the example we just saw. So we're wanting to calculate the molarity of a solution prepared by mixing 1.5 grams of NaCl, or sodium chloride, in 500 milliliters of water. So in this problem, things are a little bit different, but we can write down the equation that we had earlier. So our equation is molarity is equal to moles over liters. The problem with this equation is that in this particular problem, we're not given either of these two values. So you'll notice that we're actually given grams here, and instead of liters, unfortunately, we're given milliliters. So we've got a little bit more work to do here. This is more likely the kind of problem you would encounter. So what we'll look at, let's go ahead and write down the amount of grams that are given to us. So we've got 1.5 grams of sodium chloride, or NaCl. And what we'll need to do is obtain the number of moles of this solute. So we're basically just going to do a gram to mole chemical conversion. So we'll make a little conversion chart. Grams of sodium chloride on top, so we'll put grams of sodium chloride in the denominator so it cancels, and then we'll put moles of sodium chloride in the numerator. So for this conversion factor here, we just need to know how many grams are in 1 mole of NaCl. So we'll put a 1 up here, and if we were to look at our periodic table, you would see that sodium, its molar mass is around 23, and chlorine's molar mass is around 35. So we'll have 58. So we'll plug in 58 down here in our numerator, or I'm sorry, our denominator, and then we'll just do a quick calculation here. So again, we'll take 1.5 and we'll divide it by 58, and we end up getting, see if we can get both of this in the frame here, 0.026. We'll round it off there. And then we'll write moles of NaCl. So this is good so far because, again, we started with grams, but now we have moles. So we're halfway there. The other issue with this problem is that we're given milliliters. And again, we mentioned earlier that you have to have liters. So the number of milliliters given was 500. So we got 500 milliliters, and again we're going to do another unit conversion chart. Milliliters on top, we'll put milliliters on bottom in the next part of the chart. And we're trying to get to liters. Now, chemical conversion you probably used quite a bit throughout the year is that 1 liter is equal to 1,000 milliliters. So again, we're just going to use this, this conversion. So I'll put 1 liter in my numerator. In my denominator, I'll put 1,000. So for this particular problem, I'll be dividing 500 by 1,000, or moving the decimal place 3 places to the left. So I'll end up with 0.5 liters. So at this point in the problem, we can actually apply the formula. So we will take our moles and put that in our numerator, and we'll divide it by the number of liters, because molarity again is an expression of concentration, and it's the moles of solute per liter of solution. So we'll just do a quick calculation here. 0.026 divided by 0.5, and now we have the molarity. So our answer to this problem is going to be 0.052 molar. And we'll represent this with a capital M. Okay, so hopefully that was helpful.